Look at the empty space around you. It appears utterly vacant, a silent and transparent backdrop to our daily lives. We move through it, measure our days within it, and build our entire perception of reality upon it. Over the past century, humanity has decoded the genetic blueprint of life, dispatched robotic explorers beyond the edge of our solar system, and mapped billions of distant galaxies across cosmic history. Yet, beneath our greatest scientific triumphs lies an unsettling paradox. We still do not truly understand what this cosmic fabric actually is. Modern physics rests upon two monumental pillars. General relativity describes spacetime as a smooth, continuous fabric that curves and stretches under the influence of massive objects, giving rise to the phenomenon of gravity. Quantum mechanics, on the other hand, reveals a microscopic realm defined by discrete packets of energy, inherent probabilities, and chaotic fluctuations. Both theories have passed every experimental test with extraordinary precision. However, when theoretical physicists attempt to combine them to describe the fundamental geometry of reality, the mathematical equations collapse into meaningless infinities. Is space-time an unbroken continuum? Or is it woven from indivisible microscopic building blocks? Could space and time themselves be an illusion, emerging from deeper, non-spatial quantum connections? While numerous theoretical frameworks have been proposed to resolve this tension, empirical proof remains beyond our current reach. The foundational arena of our universe remains physics' deepest unsolved mystery. Today, we will explore why we don't understand spacetime yet. To truly grasp why modern science finds itself at a conceptual crossroads, we have to look back at how our perception of the cosmos was originally built. For centuries, classical physics offered a worldview that aligned neatly with human intuition. Sir Isaac Newton formulated a mechanical universe governed by clear deterministic laws. In this Newtonian framework, space and time were viewed as absolute, rigid, and entirely independent of one another. Space was envisioned as an infinite, empty, three-dimensional stage upon which the grand drama of the cosmos unfolded. It was a fixed coordinate grid, unaffected by the presence, motion, or interactions of the matter placed inside it. If you removed every star, planet, and atom from existence, the rigid box of Newtonian space would simply persist, undisturbed and empty. Time, in this classical picture, was equally unyielding. Newton described absolute, true, and mathematical time as flowing equably without relation to anything external. A cosmic clock was imagined to tick at the exact same rate everywhere in the cosmos, whether you were standing on the surface of Earth, drifting in the void between galaxies, or travelling at unimaginable speeds. Under this paradigm, gravity was described as a mysterious, instantaneous pull. The sun exerted an invisible force across millions of miles of empty void, holding planets in their designated orbits through an action at a distance that even Newton privately acknowledged was deeply puzzling. Yet, for over 200 years, this elegant model seemed nearly infallible. It successfully predicted the paths of celestial bodies, explained ocean tides, and guided the early industrial era. However, toward the end of the 19th century, subtle cracks began to form in this clockwork framework. When James Clerk Maxwell consolidated the laws of electricity and magnetism, his equations revealed that electromagnetic waves travel through a vacuum at a constant, finite speed, approximately 186,000 miles per second. This discovery presented a profound crisis. According to Newtonian mechanics, if you run alongside a beam of light, its speed relative to you should decrease. Yet, Maxwell's equations suggested that the speed of light remains constant for all observers, regardless of their own state of motion. Albert Einstein resolved this conflict in 1905 with his special theory of relativity, effectively dismantling the foundation of absolute space and time. Einstein proposed two deceptively simple postulates. The laws of physics are identical in all inertial reference frames, and the speed of light in a vacuum is universally constant for all observers. To preserve the constancy of this cosmic speed limit, our classical notions of distance and duration had to be radically overhauled. Space and time could no longer be treated as detached, rigid absolutes. Instead, they had to be flexible. Special relativity demonstrated that when an object moves at velocities approaching the speed of light, astonishing physical transformations occur. From the perspective of a stationary observer, the moving object undergoes measurable length contraction, shrinking along its direction of travel. Simultaneously, time undergoes dilation. Clocks on the moving object tick significantly slower compared to stationary clocks. Furthermore, the concept of absolute simultaneity collapsed. Two astronomical events that appear to happen at the exact same instant to one observer can occur at entirely different times to an observer moving relative to the first. Space and time were no longer separate entities. They were permanently fused into a dynamic, four-dimensional continuum known as spacetime. While special relativity unified space and time, it only applied to observers in uniform, unaccelerated motion and could not account for gravity. Einstein spent an entire decade wrestling with this limitation, ultimately unveiling his general theory of relativity in 1915. This theory delivered an even more revolutionary shift in our understanding. Einstein realized that gravity is not an invisible, instantaneous force pulling across empty space. Instead, gravity is the physical manifestation of the curvature of four-dimensional spacetime itself. The theoretical physicist John Archibald Wheeler later captured this profound insight in an iconic phrasing. Spacetime tells matter how to move, and matter tells spacetime how to curve. When an object possessing mass or energy is placed within the cosmos, it warps and distorts the geometrical fabric surrounding it. A massive body like our Sun creates a profound depression in the surrounding spacetime continuum. The planets in our solar system do not follow curved orbits because a mysterious tether pulls them toward the Sun. They are simply traversing the straightest possible paths, known as geodesics, through a curved, four-dimensional geometry. This model transformed our understanding of the universe from a static arena into an active, participating medium. Spacetime can be stretched, compressed, twisted, and rippled. When massive astronomical bodies such as binary neutron stars or colliding black holes accelerate violently, they generate ripples in the very geometry of the cosmos, known as gravitational waves. These waves travel through the universe at the speed of light, squeezing and stretching the fabric of reality itself. General relativity has successfully passed every experimental challenge designed to test its limits over the past century. During a solar eclipse in 1919, Sir Arthur Eddington measured the deflection of starlight passing near the Sun, confirming that mass indeed bends the trajectory of light through curved spacetime. Modern global positioning systems provide continuous, practical validation of this framework. The atomic clocks aboard orbital satellites experience both time dilation due to their orbital speed and an opposing gravitational time shift due to Earth's weaker gravitational field at higher altitudes. If engineers did not continuously calibrate these satellites to compensate for general and special relativity, civilian location data would drift by several miles every single day. Einstein's framework fundamentally replaced the static, passive container of classical mechanics with a vibrant, pliable fabric. Yet, this extraordinary triumph carried a hidden tension. General relativity models spacetime as an unbroken, continuous, and infinitely smooth mathematical manifold. It assumes that you can zoom into any point in the universe and find space to be completely smooth and deterministic, no matter how small the scale. While this smooth continuum perfectly describes the grand movements of planets, stars, and expansive cosmic structures, it assumes an idealized world where quantum fluctuations do not exist. As science began peering into the subatomic realm, this smooth picture of the universe began to encounter insurmountable barriers. While Albert Einstein was fundamentally reshaping our macroscopic understanding of the cosmos with the smooth geometry of general relativity, a parallel revolution was unfolding at the opposite extreme of physical scale. The pioneers of quantum mechanics were peering directly into the microscopic heart of matter, uncovering a subatomic realm that directly contradicted classical intuition. In this microscopic domain, nature does not behave like a predictable, continuous mechanism. Instead, it operates through discrete packets of energy, intrinsic uncertainties, and probabilistic interactions. At the core of quantum theory lies the realization that energy, charge, and angular momentum are quantized. They do not vary continuously across an infinite spectrum. Rather, they exist in distinct, indivisible units called quanta. This foundational principle was successfully expanded over the 20th century into quantum field theory and consolidated into the standard model of particle physics. Within this robust framework, matter and forces are described not through geometric curvatures, but as excitations of fundamental quantum fields permeating the universe. The standard model successfully accounts for 3 of the 4 fundamental forces of nature: the electromagnetic force, which governs interactions between charged particles, the strong nuclear force, which binds atomic nuclei together, and the weak nuclear force, which drives specific radioactive decays. In these quantum field theories, forces are mediated through the continuous exchange of messenger particles known as gauge bosons, such as photons and gluons. These interactions are fundamentally localized, discrete, and inherently probabilistic. A defining characteristic of the quantum domain is Werner Heisenberg's uncertainty principle. This principle establishes that certain pairs of complementary physical variables, most notably position and momentum, cannot both be measured simultaneously with arbitrary precision. The more precisely the spatial position of a particle is determined, the less accurately its momentum can be known, and vice versa. An analogous uncertainty relationship governs energy and time. Over vanishingly small intervals of time, the local energy of a system can fluctuate dramatically. As a direct consequence of this principle, empty space in quantum theory is never truly void. The quantum vacuum is not a serene passive vacuum, but a dynamic sea filled with spontaneous quantum fluctuations. Virtual particles and antiparticles continuously materialize from the vacuum, interact for imperceptible fractions of a second, and mutually annihilate back into nothingness. When physicists calculate the behavior of these particles using quantum electrodynamics, they frequently encounter mathematical infinities. However, quantum field theorists developed a mathematical technique known as renormalization. By systematically subtracting these infinite values using experimentally verified parameters such as the observed mass and charge of an electron, physicists can extract finite, astonishingly precise predictions that match experimental observations to more than 10 decimal places. The profound crisis in modern physics arises when theorists attempt to apply these identical quantum rules to gravity and the geometry of spacetime. In general relativity, spacetime is assumed to be a continuous, infinitely smooth mathematical manifold. It possesses no granular texture, no indivisible components, and no fundamental lower limit to measurement. In principle, according to classical relativity, one could zoom in indefinitely on any point in spacetime and continue to find a completely smooth, unbroken continuum. When you attempt to merge this smooth geometric description with quantum field theory, catastrophic mathematical contradictions emerge. According to general relativity, any concentration of energy curves the surrounding spacetime. In the quantum realm, however, the uncertainty principle dictates that as you examine increasingly smaller regions of space, the energy fluctuations become progressively more violent and concentrated. At subatomic distances, the energy density within these localized fluctuations theoretically skyrockets toward infinity. Because mass and energy dictate the curvature of spacetime, these extreme microscopic energy fluctuations would inevitably induce violent, chaotic distortions in the local geometry itself. At microscopic dimensions, spacetime would no longer resemble a smooth, predictable sheet. Instead, it would buckle, twist, and tear under the influence of its own fluctuating quantum energy. When theoretical physicists attempt to calculate gravitational interactions at these microscopic scales using standard perturbative quantum field theory, the mathematical framework completely breaks down. Unlike the infinities encountered in electromagnetism or the nuclear forces, the infinities generated by quantum gravity are fundamentally non-renormalizable. In a non-renormalizable theory, attempting to cancel one infinite value requires introducing a new arbitrary parameter into the equations. When you calculate the next level of particle interaction, another distinct infinity appears, demanding yet another arbitrary correction factor. This recursive cycle continues indefinitely, requiring an infinite number of untestable parameters to make a single physical prediction. In theoretical physics, when a mathematical model yields uncontrollable infinities across all possible configurations, it signifies that the underlying foundational assumptions are either incomplete or fundamentally incorrect. This conceptual collision represents the deepest rift in theoretical physics. General relativity is fundamentally deterministic and geometric. It requires a smooth, continuous spacetime manifold to define trajectories, horizons, and gravitational interactions. Quantum mechanics, conversely, is intrinsically probabilistic, discrete, and non-local, functioning against a static background clock where spacetime itself does not actively fluctuate. To illustrate this incompatibility, consider what happens when you attempt to determine the precise gravitational field generated by an electron passing through a double-slit experiment. Quantum mechanics demonstrates that until an observation occurs, the electron exists in a state of spatial superposition, passing through both slits simultaneously as a wave of probability amplitudes. If general relativity is strictly correct, how does the gravitational field respond to a particle that does not occupy a single definite location? Does the curvature of space-time itself enter a quantum superposition, warping in two distinct configurations at once? General relativity possesses no mathematical mechanism to accommodate such probabilistic geometries, while quantum mechanics lacks the geometric tools to account for dynamic spacetime warping. Furthermore, this mathematical conflict reaches an impassable wall at a critical threshold, known as the Planck scale. Named after the German physicist Max Planck, these natural units define the theoretical boundary where our current physical laws cease to provide meaningful answers. The Planck length measures approximately 1.6 times 10 to the negative 35 meters, while the Planck time is roughly 5.4 times 10 to the negative 44 seconds. At scales larger than the Planck threshold, the smooth approximations of general relativity function with exceptional accuracy. Similarly, across typical subatomic dimensions, the flat background spacetime of the Standard Model operates without significant error because gravitational effects between tiny subatomic particles are extraordinarily weak compared to the other fundamental forces. However, when physical conditions force substantial mass and energy into a region smaller than the Planck length, such as during the earliest moments of the universe or at the deep core of a gravitational singularity, both theories demand authority simultaneously. Under these extreme conditions, general relativity predicts infinite curvature and infinite density, while quantum mechanics predicts infinite vacuum energy and violent geometric fluctuations. The equations fail, our physical variables diverge to infinity, and our ability to describe reality evaporates. The continuous spacetime of Einstein and the discrete quantum world of Planck cannot both be fundamentally correct in their current formulations. One or perhaps both of these monumental achievements must be an approximation of a deeper, yet undiscovered physical framework. Confronted by the catastrophic breakdown of standard mathematics at the Planck scale, theoretical physicists began exploring radical frameworks to bridge the divide between quantum mechanics and general relativity. The most extensively researched and mathematically sophisticated of these approaches is string theory. Rather than treating fundamental constituents of nature as zero-dimensional point-like particles, string theory proposes an entirely different foundation. The ultimate building blocks of the universe may be tiny, one-dimensional vibrating filaments of energy known as strings. In conventional quantum field theory, particles such as electrons, quarks, and photons are treated as mathematical points with zero spatial volume. While this idealization works exceptionally well across atomic and subatomic scales, it is precisely the assumption of zero-dimensional points that generates uncontrollable mathematical infinities when gravitational interactions are introduced. When two-point particles approach each other with zero separation distance, classical equations dictate that the gravitational force between them surges toward infinity. String theory attempts to bypass this mathematical pathology by introducing a fundamental minimum length. In this framework, a fundamental entity is not an infinitely small point, but an extended one-dimensional strand that possesses length, roughly estimated to be near the Planck scale of 10 to the negative 35 meters. A string can exist as an open segment with two endpoints, or as a closed loop. Just as the distinct resonant vibrations of a violin string produce different musical notes, the distinct vibrational modes and harmonics of these fundamental strings manifest as the various particles observed throughout nature. An electron is hypothesized to be a string oscillating in one particular pattern, a quark vibrates in another, and a photon in yet another. Crucially, when theorists analyzed the vibrational spectra of closed loops within this mathematical framework, they made an extraordinary discovery. One specific vibrational mode corresponds precisely to a massless particle with a spin of 2. In quantum field theory, a massless spin 2 particle is the exact theoretical description of the graviton, the hypothetical quantum messenger particle of gravity. For the first time, a quantum mechanical model naturally produced a candidate for gravitational interaction without being manually inserted into the equations. Within string theory, gravity does not appear as an incompatible anomaly. Rather, the theory mathematically requires the existence of gravity to remain self-consistent. The hypothetical graviton represents a crucial piece of this grand puzzle. In standard quantum electrodynamics, the electromagnetic attraction or repulsion between two electrons is described by the exchange of virtual photons. By theoretical analogy, quantum gravitational interaction would be mediated through the exchange of gravitons. Because these hypothetical particles would possess zero mass, the gravitational force can extend infinitely across cosmic distances, diminishing with the square of the distance. Because strings possess physical extension rather than zero volume, interactions between incoming and outgoing strings are smeared out over smooth geometric tubes called world sheets. This structural smoothing eliminates the dangerous point-like collisions that produce uncontrollable infinities in traditional calculations, yielding mathematically finite predictions for quantum gravitational scattering. However, this mathematical elegance introduces profound conceptual challenges and dramatic departures from conventional physics. Chief among these requirements is the necessity of extra-spatial dimensions. When physicists formulated string theory within the standard framework of 3 spatial dimensions and 1 temporal dimension, the underlying quantum equations suffered from anomalies and produced negative probabilities, which are physically meaningless. To preserve mathematical consistency and preserve fundamental physical symmetries, the equations strictly dictate that strings must vibrate across additional dimensions. In its modern formulation known as superstring theory, which incorporates supersymmetry between matter particles and force carriers, the mathematical consistency requires a 10-dimensional space-time, 9 dimensions of space and 1 of time. An overarching theoretical framework introduced by Edward Witten, termed M-theory, unifies several distinct formulations of string theory and extends this requirement to 11 dimensions. Because our everyday experience and macroscopic scientific instruments reveal only 3 spatial dimensions, length, width, and height, the extra spatial dimensions must be explained. Theorists hypothesize that these additional spatial directions are compactified, curled up into extraordinarily compact geometric manifolds at scales so minuscule that they evade detection by our most advanced particle colliders. The precise geometrical shapes of these hidden dimensions are mathematically described as Calabi-Yau manifolds. The specific geometry and topological configuration of these curled-up dimensions are theorized to dictate the physical properties of our observable universe. The way extra dimensions are folded determines the vibrational patterns accessible to strings, thereby theoretically fixing the masses of fundamental particles, the strengths of the fundamental forces, and the fundamental constants of nature. However, mathematical analyses reveal that there are at least 10 to the 500th power possible ways to compactify these Calabi-Yau spaces. Each distinct geometric configuration yields an entirely different set of local physical laws, creating a vast theoretical landscape of possible universes known as the string theory landscape. Despite its mathematical sophistication, string theory faces intense debate and critical skepticism within the scientific community, primarily due to its lack of direct empirical verification. Because strings and compactified dimensions are hypothesized to reside near the Planck scale, testing their existence directly would require particle accelerators operating at energy levels trillions of times greater than the capabilities of the Large Hadron Collider. No human-built instrument has detected a single graviton, identified supersymmetric partner particles, or observed physical evidence of extraspatial dimensions. Consequently, cautious physicists emphasize that string theory must currently be classified as a mathematical hypothesis and theoretical framework rather than an established physical fact. Critics argue that without clear, falsifiable experimental predictions, the theory risks drifting into pure mathematical philosophy. Proponents, however, contend that its unmatched ability to naturally incorporate both the standard model forces and a quantum description of gravity within a single unified framework suggests that it reflects deep underlying truths about reality. Moreover, string theory fundamentally challenges our understanding of spacetime by suggesting that the geometry of the cosmos might not be a fixed background, but a secondary phenomenon. In certain configurations, such as dualities, where a universe with a large radius is mathematically indistinguishable from a universe with a tiny radius, the concept of distance itself becomes relative and ambiguous. Spacetime in string theory may simply be an effective, large-scale approximation that appears smooth only because our macroscopic perspective cannot resolve the intricate, vibrating threads and hidden multidimensional spaces humming beneath the surface of reality. While string theory seeks to unify all fundamental forces by introducing vibrating filaments and hidden extra dimensions, another prominent school of thought takes a fundamentally different path. Known as loop quantum gravity, this theoretical framework does not attempt to explain all of matter and energy in a single grand equation. Instead, it focuses directly on the central lesson of Albert Einstein's general relativity. Gravity is not a traditional force traveling across a fixed stage. Gravity is the dynamic geometry of spacetime itself. To appreciate the radical nature of loop quantum gravity, one must recognize a critical distinction in theoretical physics: background dependence versus background independence. Most standard physical theories, including the standard model of particle physics and early formulations of string theory, are background dependent. They assume that an underlying, pre-existing coordinate grid of space and time is already established, acting as a passive arena through which particles move and interact. General relativity, however, is fundamentally background independent. There is no fixed metric or static background stage. The geometry of spacetime dynamically shifts, bends, and responds to matter. Loop quantum gravity adheres strictly to this principle of background independence. Developed by physicists such as Abhay Ashtekar, Carlo Rovelli, and Lee Smolin, the theory proposes that we should not quantize particles moving within a pre-existing spacetime. Instead, we must quantize spacetime itself. In this view, space is not a smooth, infinitely divisible continuous fabric. If you were to zoom in past the atomic nucleus, past the smallest subatomic quarks, down to the absolute boundary of the Planck length, 10 to the negative 35 meters, the continuous illusion of space dissolves completely. According to loop quantum gravity, space is granular. It is composed of discrete, indivisible units of volume and area. Just as a digital photograph appears continuous from a distance but reveals individual pixels under close inspection, the fabric of our universe is theorized to be pixelated at the Planck scale. You cannot have a volume of space smaller than the fundamental Planck volume, nor can you measure an area smaller than the minimal Planck area. There is a fundamental limit to how finely reality can be divided. The mathematical formulation of this discrete geometry relies on structures known as spin networks, pioneered theoretically by Roger Penrose and later integrated into loop quantum gravity. A spin network is a mathematical graph consisting of one-dimensional lines, or edges, that intersect at specific vertices, or nodes. In this model, the nodes do not exist inside space. Rather, each node represents an elemental quantum packet of volume. The lines connecting these nodes represent quantized units of surface area. When these spin networks evolve and transform over time, they trace out four-dimensional structures known as spin foam. In the framework of spin foam, time loses its smooth, uninterrupted flow. Instead, temporal progression is described as a sequence of discrete quantum transitions, instantaneous structural rearrangements of the underlying spin network. Spacetime, in this mathematical picture, is literally woven from an interconnected, shifting web of geometric loops. This microscopic picture gives rise to the concept of quantum foam, a term originally coined by John Archibald Wheeler to describe the violent, turbulent state of geometry at the Planck scale. In classical general relativity, space at very short distances remains entirely smooth, predictable, and calm. But when quantum uncertainty is applied directly to the geometry of the continuum, the metric of space fluctuates wildly. At 10 to the negative 35 meters, the classical concepts of up, down, left, right, before and after become fuzzy and unstable. Geometry boils into a chaotic froth of microscopic fluctuations where tiny quantum topology changes can occur and localized geometries fluctuate unpredictably. Spacetime is no longer a static stage, nor even a gently undulating trampoline. It is a roiling, microscopic storm of interconnected quantum states. Loop quantum gravity offers compelling potential solutions to some of the most stubborn paradoxes in physics. In classical general relativity, when a massive star collapses under its own weight, the mathematics predicts that it will compress into a point of zero volume and infinite density, a gravitational singularity. However, if space is composed of indivisible geometric quanta, infinite compression is physically impossible. You cannot compress matter into a region smaller than the minimal quantum unit of volume. When matter is squeezed down toward the Planck density, the discrete geometry of loop quantum gravity generates a powerful repulsive quantum pressure. Instead of collapsing into a mathematical singularity of infinite density, the collapsing matter theoretically reaches a fundamental limit and rebounds. In the context of early universe cosmology, this framework gives rise to the concept of loop quantum cosmology, where the Big Bang is replaced by a big bounce. In this scenario, a prior contracting universe collapsed under gravity until it hit the discrete Planck barrier, where the quantum geometric repulsion triggered a colossal expansion, creating the observable universe we inhabit today. Despite these mathematically compelling attributes, loop quantum gravity remains a theoretical model subject to intense debate and significant unresolved challenges. One major theoretical hurdle is the sequential limit. Physicists must rigorously demonstrate that when billions of these tiny discrete loops interact on macroscopic scales, they smoothly reproduce the standard continuous equations of classical general relativity and Newtonian gravity. While significant progress has been made, completing this mathematical bridge remains a work in progress. Furthermore, like string theory, loop quantum gravity suffers from an acute lack of direct experimental verification. Probing a spatial distance of 10 to the negative 35 meters requires observational energies that far exceed anything modern human engineering can produce. Direct observation of an individual spin network node or Planck-scale geometric pixel remains completely inaccessible. Physicists pursuing loop quantum gravity are therefore looking for subtle, indirect astrophysical signatures. One speculative possibility is that if space is truly discrete, the vacuum of space might exhibit minuscule amounts of Lorentz invariance violation or energy-dependent dispersion. Under this hypothesis, extremely high-energy photons emitted by distant cosmic phenomena, such as gamma-ray bursts billions of light-years away, might travel at very slightly different speeds compared to lower-energy photons as they interact with the granular texture of quantum space. While various astronomical observations using space telescopes have placed strict constraints on these deviations, definitive proof of spatial granularity has not been confirmed. Thus, loop quantum gravity stands as a profound, mathematically rigorous alternative to string theory. It does not demand extra dimensions or unobserved supersymmetric particles, focusing instead on quantizing the very fabric of four-dimensional space. Yet both frameworks leave us with the same haunting reality. At the most fundamental scale, the smooth, reliable stage of spacetime completely disintegrates into a realm of discrete, fluctuating quantum structures that continue to defy our complete comprehension. To confront the true limits of our understanding of spacetime, theoretical physics must journey to the most extreme environments in the universe, black holes. These cosmic titans are not merely astronomical curiosities. They represent natural laboratories where the mathematical machinery of general relativity and quantum mechanics are forced into direct, catastrophic collision. At the boundary and heart of a black hole, the foundational principles that govern reality begin to unravel, exposing the deepest paradoxes in modern science. According to classical general relativity, a black hole forms when an enormous mass is compressed into an extraordinarily small region of space. When the inward gravitational pull overwhelms all known repulsive nuclear forces, the matter collapses indefinitely. Surrounding this collapsed mass is a boundary known as the event horizon. The event horizon marks the mathematical point of no return. Within this spherical perimeter, the escape velocity exceeds the speed of light. Because nothing can travel faster than light in a vacuum, no particle, light ray, or physical signal can ever escape back into the outer universe once it crosses this invisible threshold. Under classical relativity, the structure of spacetime outside the event horizon remains smooth and well-behaved. However, as an object falls inward past the horizon, the roles of space and time undergo a bizarre, unidirectional transformation. The radial spatial coordinate pointing toward the center becomes time-like. Moving toward the central core is no longer a spatial choice, it becomes as inevitable as moving forward into tomorrow. At the very center of this classical solution lies the gravitational singularity. At the singularity, general relativity predicts that matter is crushed into zero volume, causing the density, gravitational forces, and space-time curvature to surge to infinity. In classical physics, an infinity is not a tangible physical quantity. It is a clear indicator that the mathematical model has broken down. General relativity effectively predicts its own demise, signaling that at these extreme densities, the assumption of a smooth, continuous space-time manifold cannot be the complete story. To comprehend what truly exists at the core of a black hole, quantum mechanics must be brought into the equation. The profound crisis surrounding black holes escalated dramatically in 1974, when the British physicist Stephen Hawking applied quantum field theory to the curved space-time surrounding the event horizon. Prior to Hawking's groundbreaking calculation, black holes were believed to be purely absorbent entities from which absolutely nothing could emerge. Hawking demonstrated that when quantum vacuum fluctuations are considered near the horizon, a startling physical mechanism arises. As established by the uncertainty principle, the vacuum of space is perpetually bubbling with virtual particle-antiparticle pairs that continuously materialize, interact, and annihilate. Hawking calculated that when such a pair materializes precisely along the boundary of the event horizon, a remarkable event can occur. One of the virtual particles, carrying negative energy relative to an observer at infinity, falls past the event horizon into the black hole. Its partner particle, carrying positive energy, remains on the outside and escapes into the surrounding cosmos as real thermal radiation. To an outside observer, the black hole appears to emit a steady, faint glow of particles now known as Hawking radiation. Because the particle falling into the black hole possesses negative energy relative to infinity, the black hole steadily loses mass. Over unimaginably long cosmic timescales, if a black hole does not consume additional matter to sustain its mass, it will slowly evaporate, shrinking continuously until it eventually disappears entirely in a final energetic burst. While Hawking radiation represents one of the most celebrated theoretical insights in modern physics, it precipitated an existential dilemma known as the black hole information paradox. This paradox strikes at the very heart of physical law, pitting a core tenet of general relativity against the foundational axiom of quantum mechanics, the principle of unitarity. In quantum mechanics, unitarity dictates that the total probability of all possible outcomes for any physical process must always equal precisely 1. A critical mathematical consequence of unitarity is that quantum information can never be created or destroyed. If you possess complete, perfect knowledge of the quantum state of a closed physical system at any given moment, the deterministic laws of quantum mechanics allow you to calculate both its exact future evolution and reconstruct its complete historical past with absolute precision. Even if you were to incinerate an encyclopedia, the information contained within its pages is not fundamentally erased. In principle, if you collected every scattered photon, smoke molecule, and thermal vibration, the original text could be mathematically reconstructed. However, Hawking's initial superclass calculations indicated that Hawking radiation is entirely thermal and random. Its spectrum is determined solely by the gross macroscopic properties of the black hole, its mass, charge, and angular momentum. This is known in physics as the no-hair theorem. Regardless of what kind of complex matter falls into a black hole, whether it is an encyclopedia, a dying star, or a highly ordered quantum computer, the radiation emitted during the evaporation process appears completely featureless and uncorrelated. This creates an irreconcilable conflict. If a black hole completely evaporates away, and the escaping Hawking radiation contains no trace of the specific quantum states that formed it, then all the quantum information that crossed the event horizon is permanently wiped out from the universe. A pure quantum state has irreversibly transformed into a mixed thermal state. If information can truly be annihilated, the principle of unitarity fails, the deterministic foundation of quantum mechanics collapses, and our standard understanding of microscopic physics falls apart. Conversely, if information is not destroyed and somehow escapes within the Hawking radiation, another fundamental rule is violated, the equivalence principle of general relativity. The equivalence principle asserts that an astronaut falling through the event horizon of a massive black hole should experience nothing locally unusual at the horizon itself. The horizon should feel like ordinary, empty, locally flat spacetime. But for information to be transferred from the interior to the outgoing radiation, massive quantum correlations must be established right at the horizon boundary. To resolve this intense controversy, theoretical physicists have proposed a variety of radical competing hypotheses over the past several decades, none of which have achieved universal scientific consensus. One major proposal is the black hole complementarity hypothesis, formulated by Leonard Susskind, Gerard 't Hooft, and others. This model suggests that quantum information is both reflected at the horizon from the perspective of an outside observer and simultaneously passes through the horizon from the perspective of an infalling observer. Because no single observer can ever witness both phenomena at the same time without violating the cosmic speed limit, the laws of physics avoid direct contradiction. Spacetime geometry, according to this view, depends fundamentally on the observer's frame of reference. However, in 2012, a team of physicists known collectively as AMPS, Ahmed Almairi, Donald Maroff, Joseph Polchinski, and James Sully, demonstrated a major theoretical flaw in complementarity. They argued that if information truly escapes within the Hawking radiation while preserving standard quantum entanglement, the smooth spacetime at the event horizon must be replaced by a violently energetic barrier of quantum particles, a black hole firewall. An infalling observer would not drift smoothly through an empty horizon. Instead, they would be instantly incinerated the moment they touched the boundary. If the firewall hypothesis is correct, Einstein's equivalence principle and the smooth geometric description of spacetime break down completely right at the horizon, long before reaching the central singularity. Other theoretical physicists, particularly within the string theory community, explore alternatives such as the fuzzball proposal. Pioneered by Samir Mathur, this model suggests that a black hole is not an empty vacuum cavity containing a central point singularity shielded by an event horizon. Instead, it is a complex physical ball of vibrating quantum strings that extends all the way out to where the horizon would normally be. In this scenario, the event horizon is an effective macroscopic illusion. Incoming matter never encounters a true horizon or singularity, and quantum information is naturally stored and radiated away through complex string vibrations. In recent years, breakthroughs using quantum informational tools, such as the calculation of the page curve and the discovery of gravitational quantum extremal islands, suggest that information does indeed escape the black hole, preserved through subtle non-local quantum connections. Yet, calculating these pathways requires treating the interior geometry of spacetime as an entangled quantum system where spatial connectivity itself is dynamic and non-classical. The enduring struggle with black holes reveals a profound truth. We cannot understand these astronomical entities without first understanding the quantum nature of spacetime itself. Black holes push our mathematical models to their absolute breaking points, demanding that we abandon either our classical intuition of continuous, smooth geometry or our sacred quantum principles. Until a fully verified theory of quantum gravity emerges, the horizon of a black hole stands as an impassable monument to the limits of our current scientific worldview. For centuries, physics operated under the foundational assumption that space and time are the ultimate bedrock of reality. From the rigid stage of Isaac Newton to the dynamic, curving fabric of Albert Einstein, space-time was always assumed to be fundamental, a primary physical entity that cannot be broken down into simpler, non-spatial components. Yet, faced with the persistent mathematical impasse between general relativity and quantum mechanics, a growing number of contemporary theoretical physicists are exploring a radically different perspective. They propose that space-time might not be fundamental at all. Instead, it may be an emergent macroscopic phenomenon, a grand illusion arising from deeper, non-geometric quantum interactions. To comprehend what it means for something to be emergent, one can look at familiar concepts within classical thermodynamics and fluid mechanics. Consider the concept of temperature. If you isolate a single atom of helium gas floating in a vacuum, asking for the temperature of that individual atom is physically meaningless. A solitary atom does not possess a temperature. It merely possesses mass, position, and kinetic energy. Temperature only emerges when you aggregate trillions of atoms together, defining the macroscopic average kinetic energy of their chaotic collisions. Similarly, the sensation of wetness is not a property possessed by an isolated water molecule. A single molecule of hydrogen and oxygen is not wet. Wetness is an emergent property that materializes only when vast collections of water molecules interact collectively through intermolecular bonds. Theoretical physicists hypothesize that space-time itself could function in an identical manner. The smooth distances, geometric curves, and three-dimensional spaces we navigate every day might simply be the macroscopic, collective manifestations of microscopic quantum ingredients that are themselves completely devoid of space and time. If you were to zoom in far beyond the subatomic realm, past the Planck scale into the ultimate computational architecture of nature, the concept of spatial geometry might simply cease to exist. If space-time is indeed emergent, what are the underlying threads from which it is woven? A compelling and increasingly influential body of theoretical work points directly toward one of the most enigmatic phenomena in the subatomic world: quantum entanglement. Quantum entanglement occurs when two or more particles interact in such a way that their quantum states become inextricably linked, regardless of how far apart they travel. If you create an entangled pair of photons and separate them across the width of the observable universe, measuring the polarization of one photon instantly dictates the polarization of the other. Albert Einstein famously rejected the idea that physical reality could behave in this non-local manner, dismissing it as spooky action at a distance because it seemed to violate the cosmic speed limit of special relativity. However, over the past several decades, rigorous laboratory experiments, culminating in the 2022 Nobel Prize in Physics, have decisively confirmed that quantum entanglement is an undeniable, foundational fact of nature. While traditional physics viewed entanglement merely as a curious property of particles moving through a pre-existing space-time arena, modern theorists are flipping this relationship entirely on its head. They propose that entanglement is not just something that happens inside space-time. Rather, entanglement is the very mechanism that constructs and knits space-time together. A major conceptual breakthrough in this direction occurred in 2010, when theoretical physicist Mark van Ramsdonk introduced a profound thought experiment examining the relationship between entanglement and spatial geometry. Working within advanced mathematical models of quantum gravity, van Ramsdonk investigated what would happen to a smooth region of continuous space-time if you systematically altered the quantum entanglement of its microscopic components. Imagine dividing a continuous region of empty space into two distinct adjacent halves. In standard quantum field theory, these two neighboring regions are bound together by an immense degree of short-range quantum entanglement across their shared boundary. Van Ramsdonk demonstrated mathematically that if you systematically reduce and dial down the quantum entanglement between the quantum states in these two regions, an astonishing physical transformation occurs in the corresponding geometry. As the entanglement weakens, the geometric distance between the two regions effectively expands. The space-time between them begins to stretch, thin out, and narrow into a constricted neck. If you reduce the entanglement all the way to zero, completely disentangling the two regions from one another. The connecting fabric snaps. Space-time physically pinches off and tears apart, leaving two entirely disconnected, isolated universes with no spatial bridge between them. The profound implication of this mathematical thought experiment is that quantum entanglement functions as the invisible geometric glue holding the universe together. The reason 2 points in your room are close to each other, or the reason 2 galaxies can interact across cosmic voids, is fundamentally because the underlying quantum information defining those regions is deeply entangled. The smooth, uninterrupted connectivity of our physical world may simply be the macroscopic manifestation of vast, intricately organized networks of quantum entanglement humming beneath the surface of classical perception. This conceptual shift aligns closely with a broader paradigm known in modern physics as it from qubit, an evolution of John Archibald Wheeler's iconic phrase, it from bit. This framework proposes that the most fundamental constituent of the physical universe is not matter, energy, or continuous geometric space, but quantum information. In this view, particles, stars, planetary orbits, and the sweeping curvature of Einstein's gravitational fields are secondary, derived phenomena. They are macroscopic thermodynamic descriptions of complex quantum circuits and informational networks processing reality at a subgeometric layer. However, scientific rigor demands careful qualification. While the emergence of spacetime from quantum entanglement offers an extraordinarily elegant and mathematically rich narrative, it must be emphasized that this remains a theoretical hypothesis rather than an established physical law. The mathematical frameworks where these calculations are performed with absolute precision rely on highly idealized models, such as universes with negative cosmological constants that differ fundamentally from the expanding geometry of our actual cosmos. Furthermore, scientists currently possess no experimental apparatus capable of directly testing these pre-geometric quantum connections in a physical laboratory. We cannot artificially disentangle a patch of the vacuum to watch space physically tear apart, nor can we observe the non-spatial building blocks directly. Nevertheless, the hypothesis of emergent spacetime represents a monumental shift in how we approach the deepest questions of existence. It suggests that our historical failure to quantize general relativity is not merely a technical mathematical failure, but a conceptual error in our initial assumptions. We may have been trying to quantize a continuous fabric that was never truly fundamental in the first place. If space and time are emergent illusions, then understanding space-time requires us to abandon our reliance on geometric coordinates entirely, journeying into an abstract realm where reality is defined purely by quantum information, entanglement, and algebraic relations. In 1935, Albert Einstein co-authored 2 foundational scientific papers that seemed completely unrelated at the time. In the first paper, written with Nathan Rosen, Einstein explored a peculiar mathematical consequence of general relativity, the theoretical existence of bridges connecting 2 distant regions of spacetime, structures known formally as Einstein-Rosen bridges and popularly called wormholes. In the second paper, written with Boris Podolsky and Nathan Rosen, Einstein critiqued the strange non-local predictions of quantum mechanics, describing what would later become known as the Einstein-Podolsky-Rosen paradox, or quantum entanglement. For nearly 8 decades, these 2 concepts existed in completely separate branches of physics. Wormholes belonged strictly to the macroscopic, geometric realm of gravitational physics, while quantum entanglement belonged exclusively to the microscopic domain of subatomic particles. However, in 2013, theoretical physicists Juan Maldacena and Leonard Susskind proposed a bold and unexpected synthesis that reshaped theoretical physics. They encapsulated their conjecture in a simple, profound equation, ER equals EPR. This conjecture posits that the geometric bridges described by Einstein and Rosen and the quantum entanglement described by Einstein, Podolsky and Rosen are not merely analogous, they are fundamentally the exact same physical phenomenon viewed through different theoretical lenses. According to this hypothesis, whenever 2 quantum particles become entangled, they are not simply communicating across an empty void through mysterious non-local correlations. Instead, they are physically connected by a microscopic, non-traversable wormhole tunneling through the underlying fabric of spacetime, Under the ER equals EPR framework, what we perceive as macroscopic space is essentially constructed from an immense interconnected web of microscopic quantum tunnels. If you take an isolated collection of particles and thoroughly entangle them with another distant collection, the individual microscopic wormholes linking each particle pair coalesce into a large continuous geometric shortcut through space. In this speculative picture, gravity and spatial geometry do not exist as primary physical entities. Rather, geometry is a macroscopic manifestation generated by the complex entanglement of quantum information. This radical unification of geometry and quantum entanglement is intimately tied to another revolutionary concept, the holographic principle. The roots of this idea trace back to the 1970s, when physicists Jacob Bekenstein and Stephen Hawking investigated the thermodynamic properties of black holes. In everyday classical physics, the maximum amount of information a container can hold scales directly with its three-dimensional volume. If you double the length, width, and height of a storage drive, its data capacity increases eightfold. Yet, when Bekenstein and Hawking calculated the maximum entropy, or information capacity, of a black hole, they discovered something extraordinary. The entropy of a black hole does not scale with its three-dimensional volume. Instead, it scales strictly with the two-dimensional surface area of its event horizon. Mathematically, the event horizon acts like an informational boundary, where one bit of information is stored for every 4 fundamental Planck areas. In the 1990s, Gerard 't Hooft and Leonard Susskind generalized this profound insight to the entire universe, formulating the holographic principle. They conjectured that our perception of a three-dimensional world filled with massive objects, gravitational fields, and dynamic trajectories might be physically equivalent to a two-dimensional boundary system encoding that exact same information without any gravitational forces at all. Just as a flat, two-dimensional holographic sticker can create the convincing visual illusion of a three-dimensional image when illuminated by light, the physical reality of our three-dimensional cosmos might be an emergent projection generated by quantum interactions taking place on a distant, lower-dimensional boundary. The most concrete mathematical realization of this principle was discovered in 1997 by Juan Maldacena, known as the anti-de Sitter and conformal field theory correspondence, or ADS-CFT duality. Maldacena demonstrated mathematically that a specific 5-dimensional universe containing gravity and curved spacetime, known as anti-de Sitter space, is precisely equivalent and interchangeable with a 4-dimensional quantum field theory, living on its outer boundary, that contains no gravity whatsoever. Every physical event occurring within the interior volume, known as the bulk, can be mathematically translated into a corresponding quantum interaction occurring on the lower dimensional boundary, and vice versa. An object falling through curved gravitational spacetime in the interior corresponds exactly to a complex quantum state evolving and spreading across the boundary without gravity. The interior dimensions of space and gravitational curvature literally emerge from the quantum entanglement patterns residing on the boundary. If you calculate the entanglement between distinct regions on the boundary surface, you directly reconstruct the geometric distances and gravitational curves inside the higher dimensional universe. If the holographic principle and the ADS-CFT correspondence reflect fundamental aspects of nature, the philosophical implications for our understanding of reality are staggering. The third dimension of space, the physical depth that allows us to move forward, backward, and perceive distance, might not be a fundamental property of the universe. Instead, it may be an emergent construct, a geometric illusion generated by the collective entanglement of quantum information residing on a lower dimensional boundary. However, scientific discipline requires that we distinguish between mathematical models and empirical physical facts. While the ADS-CFT correspondence is universally celebrated for its mathematical consistency and has generated thousands of research papers, it operates within an idealized theoretical sandbox. An anti-de Sitter universe possesses a negative cosmological constant, giving it a saddle-like geometry that curves back on itself, and features a well-defined outer boundary where boundary field theories can comfortably reside. Our actual observable universe, however, behaves very differently. Astronomical observations of distant supernovae demonstrate that our cosmos has a positive cosmological constant, characterized by a de Sitter geometry that is expanding at an accelerating rate and lacks a static, well-defined spatial boundary. Translating the holographic duality from the mathematically friendly environment of anti-de Sitter space to the accelerating de Sitter universe we inhabit remains one of the most stubborn and unresolved challenges in modern theoretical physics. Moreover, like many frontier concepts in quantum gravity, the holographic principle and the ER equals EPR conjecture currently lack direct empirical verification. No telescope or laboratory detector has ever measured the holographic boundary of our cosmos or directly observed a microscopic quantum wormhole linking two entangled particles. Nevertheless, these dualities demonstrate a profound conceptual shift within the scientific community. They suggest that our century-long struggle to unite general relativity and quantum mechanics may stem from looking at the universe from the wrong vantage point. Spacetime may not be the fundamental arena where physical events take place. It may simply be the holographic projection of a deeper, non-spatial language of quantum entanglement and information. When we turn our telescopes outward and peer across billions of light years, we are not merely looking across vast spatial expanses, we are looking directly into the deep cosmic past. Because light travels at a finite speed, the most distant galaxies reveal the universe as it existed in its earliest infancy. In the late 1920s, Edwin Hubble observed that distant galaxies are moving away from us in every direction, leading to the profound realization that our universe is expanding. The fabric of space-time is continuously stretching, carrying celestial bodies along with it. If we mathematically reverse this cosmic expansion, all the matter, radiation, and space itself compress into an increasingly dense, hot, and compact state. Extrapolating classical general relativity all the way back to the beginning, approximately 13.8 billion years ago, leads to a cosmic singularity, an initial state of infinite density, infinite temperature, and infinite space-time curvature known as the Big Bang. Yet, just as in the interior of a black hole, this mathematical singularity represents a breakdown of our models rather than a definitive physical description. If classical relativity is taken literally, space-time itself, along with the very concepts of before and after, materialized at this singular boundary. Asking what occurred before the Big Bang in classical relativity is often likened to asking what lies north of the North Pole. However, when quantum mechanics is considered, an infinite singularity becomes physically unviable. At the Planck epoch, the first 10 to the negative 43 seconds after the hypothetical origin, temperatures and energy densities were so extreme that quantum gravitational effects must have dominated the geometry of the cosmos. In this primordial domain, the smooth temporal flow of classical relativity ceases to function. Did space and time truly begin at a single point? Or did the universe undergo a quantum bounce from a prior contracting phase? Some speculative theoretical models suggest that time may have transitioned from a spatial dimension into a temporal one, while others propose that space-time emerged spontaneously from a timeless quantum state. At present, because we lack an empirically verified theory of quantum gravity, science cannot definitively state what transpired at the true origin of reality. To account for the remarkable uniformity and geometric flatness of the observable universe, cosmologists introduced the hypothesis of cosmic inflation. Proposed in the early 1980s by physicists including Alan Guth and Andre Linde, inflation posits that during an imperceptible fraction of a second, between roughly 10 to the negative 36 and 10 to the negative 32 seconds after the beginning, space-time underwent an unimaginably rapid, exponential expansion. During this inflationary burst, space itself expanded faster than the speed of light. This superluminal expansion does not violate special relativity, because relativity restricts the motion of matter and information through space-time, not the physical expansion of space-time itself. In a fraction of a second, microscopic quantum fluctuations were stretched across vast cosmic distances, planting the primordial seeds of density variations that would later collapse under gravity into galaxies, stars, and planetary systems. While cosmic inflation provides an extraordinarily compelling framework that matches precision measurements of the cosmic microwave background radiation, the exact physical mechanism driving this primordial expansion remains unverified. The cosmological mystery deepened in 1998, when astronomers studying distant Type 1a supernovae discovered that the expansion of the universe is not slowing down under the collective gravitational pull of matter. Instead, cosmic expansion is actively accelerating. To explain this accelerating expansion within the framework of general relativity, cosmologists introduced the concept of dark energy. Accounting for approximately 68% of the total mass-energy budget of the observable universe, dark energy acts as a pervasive repulsive pressure embedded throughout the fabric of space. As the universe expands and more space is created, the density of dark energy does not dilute. It remains constant, steadily pushing the cosmos apart at an ever-increasing rate. The simplest mathematical candidate for dark energy is Albert Einstein's cosmological constant, an intrinsic energy density belonging to the vacuum of space. Yet, when theoretical physicists attempt to calculate the value of this vacuum energy using quantum field theory, they encounter what is widely regarded as the most catastrophic discrepancy in the history of science: the cosmological constant problem. The theoretical value derived from summing the zero-point quantum fluctuations of all known fundamental fields exceeds the experimentally measured value of dark energy by up to 120 orders of magnitude. A discrepancy of 10 to the 120th power indicates that our current mathematical understanding of the quantum vacuum and its interaction with the geometry of spacetime is profoundly incomplete. Alternative hypotheses suggest that dark energy might be a dynamic, evolving scalar field termed quintessence, or perhaps evidence that general relativity must be modified at cosmological scales. Currently, we simply do not know what constitutes the vast majority of our universe's energy. The remaining mystery of the unseen cosmos lies in the phenomenon of dark matter. In the 1930s, Fritz Zwicky observed that galaxies within the Coma cluster were moving far too fast to be held together by the gravitational pull of their visible luminous matter alone. Decades later, pioneering observations by Vera Rubin and Kent Ford revealed that the outer stars in spiral galaxies rotate at nearly the same speed as the stars near the galactic core, flatly contradicting the predictions of Newtonian gravity and general relativity based purely on visible stellar mass. Today, multiple independent lines of observational evidence, including the gravitational lensing of distant light, the detailed temperature fluctuations in the cosmic microwave background, and large-scale cosmic structure formation, confirm that approximately 27% of the universe consists of dark matter. Normal baryonic matter, the protons, neutrons, and electrons that make up every star, planet, dust cloud, and human being, accounts for barely 5% of the cosmos. Dark matter does not absorb, reflect, or emit electromagnetic radiation of any kind. We infer its presence almost exclusively because its unseen mass bends and warps the geometry of spacetime around it. For decades, the leading hypothesis has been that dark matter is composed of undiscovered non-baryonic subatomic particles, such as weakly interacting massive particles, axions, or sterile neutrinos. Yet, despite decades of sensitive searches utilizing deep underground detectors, space-based telescopes, and particle colliders, not a single direct interaction with a dark matter particle has ever been conclusively detected. This persistent experimental silence has prompted some physicists to question whether dark matter exists as a physical substance at all. Competing theoretical frameworks, such as modified Newtonian dynamics and various extended theories of gravity, suggest that dark matter phenomena might be an illusion caused by our incomplete understanding of how gravity and spacetime curvature behave over vast galactic distances. When we step back and assess modern cosmology, the resulting picture is both humbling and stark. 95% of the cosmos consists of dark components whose fundamental physical nature remains entirely unknown to science. To make our standard cosmological models function, we must invoke an inflationary beginning we cannot directly verify, a pervasive dark energy whose calculated value is impossibly contradictory, and an invisible dark matter that evades direct detection. These profound cosmic mysteries demonstrate that our understanding of spacetime is fundamentally incomplete not just at the infinitesimally small Planck scale, but across the largest observable scales of the universe. Spacetime is dynamic, expanding and shaped by forces we have barely begun to decipher. reminding us that modern physics has mapped only the visible ripples on an ocean of unknown physical reality. For all the mathematical ingenuity behind string theory, loop quantum gravity, and emergent spacetime, theoretical physics currently faces an unprecedented impasse, a profound shortage of direct empirical evidence. Throughout the history of science, revolutionary theories have survived or perished based on their ability to make testable, falsifiable predictions verified through rigorous physical experimentation. Yet, when exploring the foundational texture of spacetime, human technology runs directly into the formidable physical barrier of the Planck scale. To probe physical structures at smaller and smaller spatial distances, quantum mechanics dictates that one must utilize particles carrying progressively higher energies. The world's most powerful particle accelerator, the Large Hadron Collider, accelerates protons to energy levels exceeding 13 tera-electron volts within a subterranean ring measuring 17 miles in circumference. This monumental engineering achievement allows scientists to probe subatomic phenomena down to roughly 10 to the negative 19th meters. However, the fundamental Planck length resides at 10 to the negative 35 meters, a dimension 16 orders of magnitude smaller. To construct a traditional particle accelerator capable of concentrating enough energy to directly resolve the hypothetical granular loops or vibrating strings of spacetime, the accelerator ring would need to span the diameter of the Milky Way galaxy. Building such a machine is completely impossible under any foreseeable technological or economic constraints. Because humanity cannot construct a galaxy-sized particle collider, physicists must rely on the universe itself as a natural high-energy laboratory. One speculative method involves observing ultra-high-energy photons originating from violent cosmic cataclysms, such as gamma-ray bursts located billions of light-years away. If spacetime is fundamentally granular and characterized by quantum foam, high-energy light might interact ever so slightly with this microscopic texture, causing photons of different energies to travel at fractionally different velocities across cosmological distances. While space-based telescopes have monitored these astronomical signals for decades, any observed timing deviations have remained within standard experimental margins of error, ruling out only the simplest models of Lorentz invariance violation while leaving the broader questions unanswered. The most transformative window into the dynamics of spacetime opened in 2015 with the historic direct detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory. For the first time in history, scientists did not observe the universe purely through electromagnetic radiation. They measured the physical squeezing and stretching of spacetime itself, caused by the violent collision of two black holes over 1 billion light-years away. By utilizing laser interferometry, capable of measuring spatial distortions smaller than 1/10,000th the diameter of a proton, gravitational wave astronomy turned spacetime from an abstract mathematical backdrop into an actively measurable medium. Modern gravitational wave observatories, including LIGO, Virgo, and CAGRA, alongside Planck's next-generation detectors such as the Cosmic Explorer and the Einstein telescope, are actively searching for subtle deviations from classical general relativity. Theorists suggest that if black holes possess quantum structures near their horizons, such as firewalls, fuzzballs, or discrete quantum geometries, the gravitational wave signals emitted during and immediately following a cosmic merger might contain subtle anomalous signals known as gravitational wave echoes. While several independent research teams have analyzed public data looking for these post-merger oscillations, no definitive statistically verified signatures of quantum horizons have yet been confirmed. Looking further ahead, space-based gravitational wave detectors such as the Laser Interferometer Space Antenna, or LISA, scheduled for launch in the mid-2030s, will deploy a triangular constellation of 3 spacecraft separated by millions of miles in space. Operating entirely free from terrestrial seismic noise, LISA will be capable of detecting low-frequency gravitational waves from supermassive black hole collisions and extreme mass ratio in spirals. Furthermore, astrophysicists are actively searching for the stochastic gravitational wave background, primordial ripples generated during the earliest inflationary moments of the universe. If detected, these ancient gravitational waves could carry fossilized quantum signatures from the Planck epoch itself, offering an unprecedented glimpse into the state of spacetime when the cosmos was merely a fraction of a second old. Simultaneously, an emerging generation of tabletop quantum experiments seeks to test quantum gravity directly in the laboratory without requiring massive cosmological energies. Physicists are designing macroscopic quantum superpositions, atom interferometers, and optomechanical systems to test whether gravity can mediate quantum entanglement between massive quantum objects. If two microscopic objects in spatial superpositions become entangled purely through their mutual gravitational attraction, it would provide direct experimental confirmation that the gravitational field itself must possess quantum properties. Until these astrophysical observations or delicate tabletop experiments yield definitive data, humanity remains suspended in an era where mathematical models vastly outpace experimental validation. Spacetime keeps its secrets locked away at scales nature seems fiercely determined to protect from our observation. The fact that we do not yet understand spacetime is not an admission of defeat. Rather, it marks the grandest frontier in modern science. Throughout the history of inquiry, whenever our best mathematical models have clashed and our classical intuition has shattered, humanity has stood on the precipice of a monumental scientific revolution. The unresolved tensions between the continuous geometry of general relativity and the probabilistic world of quantum mechanics do not signal an end to physics, but the dawn of an entirely new paradigm. Just as the radical transitions from Newtonian mechanics to relativity and quantum theory completely transformed our understanding of the universe, unlocking the fundamental nature of spacetime could usher in unprecedented technological and conceptual breakthroughs. Unraveling whether space and time are fundamentally discrete, woven from quantum information, or simply emergent macroscopic illusions, will ultimately reshape our place within the cosmos. We are living through an era of profound scientific exploration, actively searching for the missing piece of nature's greatest puzzle. Thank you for journeying with us to the outer frontiers of theoretical physics. If you enjoyed this deep exploration into the mysteries of the cosmos, please feel free to like the video and subscribe to the channel for more scientific journeys. And before you go, let us know in the comments below exactly where in space and at what moment in time are you watching this right now. Until next time, keep looking deeper into the fabric of reality.